So, hello everyone, we will continue our discussion of enzyme inhibition. So, in the first part, we discussed the reversible inhibition, and in reversible mostly we discussed three different types of inhibition: competitive, uncompetitive and non-competitive. In the case of competitive, inhibitor competes with the active site of the substrate. So, in case of competitive, the target is E. In case of non-competitive, this inhibitor binds to E as well as the ES, enzyme substrate complex, but not at the active site. And in case of uncompetitive, inhibitors targets to the enzyme substrate complex. So, how to identify which type of inhibition is there? So, we have to calculate the value of Km and Vmax, and we have to compare these two values with presence and absence of inhibitor. If the Km is increased and Vm is unaffected, it is competitive inhibition. If Km is unaffected, Vm is reduced, it is non-competitive, and when both are reduced, Km and Vm, that is uncompetitive inhibition. Now, going ahead, in today's lecture, we are going to discuss substrate inhibition, allosteric inhibition, then second type of inhibition, that is irreversible inhibition, and followed by that we will see enzyme deactivation due to various environmental conditions. As enzymes are proteins, so they are susceptible to the environment. So, substrate inhibition, as I told, this is a typical enzymatic reaction. Enzyme is attaching with the substrate to form enzyme substrate complex, and further this is dissociating into enzyme and product. Now, what is happening? This substrate is further binding with enzyme substrate complex and forming ES2. So, what we can write, E plus S is ES and ES plus S is ES2. So, as you know, in the first case, dissociation constant is Km, Michaelis-Menten constant. Here we are writing dissociation constant as Ksi, because here substrate is acting as an inhibitor. So, it says high substrate concentration may cause inhibition in some enzymatic reaction, and that is known as substrate inhibition. Now, when we are discussing this, so ES2, the part, it is not participating in the product formation anymore. So, similar to this other inhibition, we should be able to write the rate equation for this as well. So, this will be V is V max, and V max is K catalytic into E naught divided by 1 plus Michaelis-Menten dissociation constant divided by S plus S upon dissociation constant of substrate inhibition. We can further rearrange this. So, this will be V max S upon Km plus S square upon Ksi. So, in this way we are able to explain the substrate inhibition behavior. Now, there could be two cases. One case at low substrate concentration, S square upon Ksi is very low. So, what will happen if you ignore this term? This simply becomes V equals V max S upon Km plus S. So, it becomes very much similar to Michaelis-Menten equation. And if you want to calculate this kinetic parameter, we have already discussed, you have to do the reciprocal of this, and then you can plot y versus x. For example, if I do simple Lineweaver work plot, it will be 1 upon V equals 1 upon V max plus Km upon V max. This is the slope into 1 upon S. This is a y axis, this is the x, this is the m, and this is the c. So, it follows the straight line, y is mx plus c. Now, second case, when substrate concentration is high, it means Km upon S is less than 1. So, in that case, this equation becomes V equals V max S upon S square upon KSI S. So, Km we have ignored here. Now, if I rearrange this, so it will become 1 upon V equals 1 upon V max plus S upon KSI into V max. So, here if I want to calculate this kinetic parameter, so we have to plot y axis will be 1 upon V, but x axis will be S in place of, and intercept will be 1 upon V and slope will be 1 upon KSI into Vm. So, in this way we calculate the kinetic parameter depending on low substrate concentration as well as the high substrate concentration. Yeah, further if you want to calculate, because if I see the typical behavior for substrate inhibition, it says rate versus substrate. With increase in the substrate concentration, rate increases, reaches to plateau, then further decreases. It means it has a maxima. And how to calculate maxima? To calculate the maxima, you have to say dV upon ds equals to 0. And if I put here dV upon ds equals to 0, so we end up with S square is Km to KSI, or S max equals under root Km KSI. So, in this way, if you know this KSI and Km, one can calculate what is the maximum concentration till which will not observe the substrate inhibition. So, typically we see when substrate concentration is increasing, this is activation step, it reaches to plateau. But when there is inhibition, it reaches to plateau, and if we increase further, there is a decrease in the rate, that is called the substrate inhibition. So, one example of substrate inhibition is substrate inhibition in a reaction catalyzed by succinate dehydrogenase, where succinate is converted to fumarate. So, succinate is converted to fumarate. So, optimal concentration, both carboxyl group of a single succinate molecule must bind to the enzyme for the reaction to proceed. So, in that case, you just see one binding site is here, other binding site is here. It requires to proceed the reaction. Now, you just see reaction rate with same Vm and Km if there is no substrate inhibition, and in the presence of substrate inhibition, it reaches to maxima and then it further declines here. So, what it says, when substrate concentration is very high, means two separate succinate molecule may bind to enzyme simultaneously here. Each molecule bind by one carboxyl group occupying both sides required for proper functioning of single substrate. And once this is done, this prevents the correct substrate binding and halts the reaction until one of the misbound substrates dissociates. And as this is hindering with the reaction, this leads to the formation of a dead end complex, and this form of inhibition may be uncompetitive or non-competitive depending on the kinetic parameter, is known as the substrate inhibition. So, what it says, in this case, even the excess substrate molecule itself act as an inhibitor. We just see this line is without inhibitor and this is with inhibitor. Yeah, next is allosteric inhibition. So, before we discuss allosteric inhibition, let us discuss allosteric enzymes. So, allosteric enzymes, we say there are few enzymes which are having more than one substrate binding site, or you can say that it is oligomeric enzymes. And what happen in this case, binding of one substrate to the enzyme facilitate the binding of other substrate molecule, and this behavior is known as allostery or cooperative binding. So, similar to this Michaelis-Menten equation, we write the rate expression for this as well, where it says ds upon dt is V max S upon Km plus S, but here we are putting a value n here to the power S, and this n is known as cooperativity coefficient. So, depending on the value of n, we decide that which type of allosteric effects are there. For example, if n is 1, this simply becomes the Michaelis-Menten equation. And if you want to calculate the value of n, what we have to do? We have to simply integrate this and then we will get this value. So, if I integrate this, you will get ln V upon Vm minus V equals n ln S minus ln Km. It is very simple, and this when you put the power n, this is called the Hill equation. Now, as I told, you can have different value of n, it may be less than 1, it may be greater than 1, or it may be n equals 1. Now, it has three different significance. When n is 1, there is no cooperativity and enzyme follows Michaelis-Menten relationship. When n is greater than 1, cooperativity is positive and the benefit from effector binding increases the value of as the value of n increases. And what will be the maximum value of n? The maximum value of n is the number of substrate binding site on the enzyme. And third case, when n is less, the cooperativity is negative and the effector binding reduces the substrate affinity and enzyme activity, means now it is acting as an inhibitor. So, depending on the value of n, we can say whether there is a cooperativity, n is greater than 1, positive cooperativity, less than 1, negative cooperativity. Now, we can understand allosteric inhibition. Allosteric inhibition occurs when an inhibitor binds to an enzyme at a site which is distinct from active site. So, unlike inhibitors that form a dead end complex, allosteric inhibition causes conformational changes in the enzyme, and when there are conformational changes, it affects the binding characteristics or affinity for the substrate, it affects reaction characteristics, the enzyme activity, or it may affect both affinity as well as the activity. Now, what are the key features for allosteric inhibition? Here again still you can do the Michaelis-Menten plot for allosteric inhibition, but you are going to see the sigmoidal shape curve rather than hyperbolic curve, which indicates the variation in the reaction rate depending on the substrate concentration. Now, as I told, the allosteric inhibition can affect the affinity for the substrate, it can affect the enzyme activity or both. So, when only one substrate binding is affected, in that case V max will remain unchanged, this mimics the cooperative inhibition, and when V max is altered, it may resume non-competitive or mixed inhibition depending on the change in the value of Km. So, again if you remember, if Vm remains unchanged, it is following competitive inhibition, and when Vm is altered, it is following non-competitive or mixed inhibition. So, you can see this is a Michaelis-Menten curve, and this is the allosteric one following a S-shaped sigmoidal curve. So, now you can remember the allosteric inhibition is common in oligomeric enzyme. Oligomeric enzyme means allosteric enzymes made of multiple subunits, often involved in feedback or in product inhibition. This control can be lost if the enzyme dissociates from individual subunit. This indicates the importance of native structure of a protein in allosteric regulation. So, basically this allosteric enzyme or allosteric inhibitors causing the conformational changes, and this conformational changes is affecting the affinity for substrate and enzyme activity. So, this up to here we discussed the reversible inhibition. Now, next we will be discussing irreversible. In case of reversible, the interaction between substrate and enzyme is through non-covalent interaction through the physical bonding, but in the case of irreversible, inhibitors bind permanently to an enzyme's active site through covalent bond. So, it blocks the enzyme by preventing the substrate binding or damaging the catalytic site. And as I told this, as this is irreversible in nature, in that case the dissociation constant value is very low, 10 to the power 9 mole inverse or even less. Now, how does it works? What it says, it has made certain portion of enzyme inactive. So, if the inhibitor concentration is I naught, so we can say active enzyme becomes E naught minus I naught. So, this is the active enzyme, and once you know this active enzyme, still we can apply the Michaelis-Menten equation. What is going to change here? V max is going to change. You know what is the V max? V max is K catalytic into E naught. So, here this E naught will be replaced by K catalytic and E naught will be replaced by E naught minus I naught. So, here if I write this V max dash and this is the V max. So, if you divide V max dash upon V max, will end up with 1 minus I naught upon E naught. So, in either way you can say the V max is V max dash is V max 1 minus I naught upon E naught. So, this is the negative part, and this much value of V max has reduced, while Km is unchanged. Further, when we are discussing with enzymes, so for bioprocess they are exposed to various environmental or operation conditions like temperature, pH, ionic strength, mechanical forces, presence of denaturant like solvent, detergent and heavy metals. And these environmental factors may have some affinity towards enzymes or proteins, and when they are able to bind at the active site of the protein, so these foreign molecules or these environmental factors also deactivates the enzyme. Because the amount of active site can decline considerably during the reaction, in many applications the kinetics of enzyme deactivation are just as important as the kinetics of reaction itself, because whenever in actual application the enzymes will be exposed to other environmental conditions. So, we can say enzyme deactivation, it occurs at the rate that is dependent on the structure of the enzyme and the reaction conditions. Now, what it says, the simplest model for enzyme deactivation is, it is going for irreversible transformation. So, this active form of enzyme is become inactive form with the deactivation rate of Kd. So, we can calculate the rate of deactivation. So, this becomes minus dEA upon dt Kd into EA. So, it simply becomes EA, first order kinetics, is equal to EA naught e to the power minus Kd into T. Now, what is happening in case of enzyme deactivation? The amount of enzyme is further decreasing, and once we know this is following the first order kinetics, and if I say half time means when the activity is half. So, it means EA upon E naught is half. If I put over here, so we will end up with T will be replaced by TH, TH is ln2 upon Kd. So, in this way, if half time is given, we should be able to calculate the deactivation rate. Now, once we know what is the change in the E, again we should be able to calculate the value of Vmax. Vmax will be K catalytic E naught e to the power minus Kd into. So, as I discussed the pH, as we know all the enzymes are made of proteins, and proteins are sensitive to the pH value, because all the physical interatomic interactions including hydrogen bond, van der Waals interaction, ionic interaction, they are all affected by the pH. Temperature, we have already discussed the Arrhenius equation, the rate increases with the temperature, but being the proteinous nature, the up to certain temperature the proteins are stable, and beyond certain temperature it denatures and unfolds, and once it denatures and unfolds, its catalytic properties are lost. Fluid forces, when you go in the bioprocess, we have the mixing, we have the fluid flow, and these exert the shear force on the protein molecule or enzymes, and in the presence of shear still it can lead to the conformational changes of the enzymes. In addition, the chemical agents, there are many chemical agents in the bioprocess which can interfere with the stability of enzymes. Even physical agents like irradiation, they can also affect the intermolecular interaction which stabilizes the native structure of a protein. So, what are the solution? The solution is one can add the stabilizing agent, one can modify the chemically, and third one is you can immobilize to prevent directly from the environment. In fact, this immobilization is the next module, that is applied enzyme catalysis. Now, we will see one example here which we discussed in the last lecture, that an enzyme reaction was found to be affected by two inhibitors A and B. Initial reaction rate in the presence of inhibitor A, B, and in the absence are given here, and the concentration of both the inhibitors was 1 millimole per liter. So, what we saw ki up to 2 to 10, when you are increasing the substrate concentration, there is increase in the reaction rate, but when you are increasing from 10 to 50, there is a decrease in the reaction rate. It means this is a substrate inhibition, and further these two parts we have discussed in the presence of inhibitor A and inhibitor B. So, what we deciphered in the presence of inhibitor A and B, we calculated the value of Vmax and Km, and if you just see based on these value we commented, this is the competitive inhibition. What do you mean by competitive inhibition? Competitive inhibition means there is an increase in the Km value and no change in the Vmax. In the case of non-competitive, what we observed was there is a decrease in the Vmax and at the same time there is no change in the Km value. So, this we discussed in the last lecture. Now, what we are going to see here is the substrate inhibition in the range of 10 to 50 millimole per liter. So, if you just see here in the range of 10 to 50 millimole per liter. So, in this range we are observing the substrate inhibition, and once this is substrate inhibition, this is the equation, this can be rearranged like this. So, we have to plot 1 upon V and S. So, the intercept will be one upon V max and the slope is 1 upon V max KSI. So, particularly for this case, the slope is coming out, slope is 0.02 and intercept 0.53. So, it means Vm becomes 1.89 and from the slope we can calculate the value of KSI, this will be 28.09. Once we know the KSI, Km we have already calculated here, that in the absence of inhibitor the value of Km was 6.65. So, we can calculate the value of S max. S max, if you remember, it is KSI into Km, and if I found calculate, this value is 13.68 millimole per liter. So, if I just see here substrate and rate will increase like this, reach to plateau and this value is coming out to be 13.68. I will see one more example where we are discussing effect of enzyme deactivation. So, it says lipase is being investigated and as an additive to laundry detergent for the removal of stains from fabric. The general reaction is fat is converted to fatty acid and glycerol. The Michaelis constant for pancreatic lipase is 5 millimolar. At 60 degree centigrade, lipase is subject to deactivation. So, here what is the factor for deactivation is temperature with a half time of 8 minutes. So, half time is given 8 minutes, from there we can calculate the rate of deactivation. So, it says TH is ln2 divided by Kd. Fat hydrolysis is carried out in a well mixed batch reactor that simulates a top loading washing machine. The initial fat concentration is 45 gram mole per meter cube. At the beginning of reaction, the rate of hydrolysis is 0.07 millimole per liter per second. So, it says how long does it take for the enzyme to hydrolyze 80% of the fat. So, what will be the S? Final S will be 0.2 S naught. So, this will be, it was 45, so this will be 9 mole per meter cube. Now, this example we can solve in two ways. In one case, we can consider there is a enzyme deactivation, in other case there is a no deactivation. So, first let us note down the given parameter there. So, it says Km is 5 millimole, this will become 5 mole per meter cube. S naught is 45 mole per meter cube. S is 20% of this is 9 mole per meter cube, and Kd we have calculated. Kd is ln 2 upon Th. Th was 8 minutes, so it become 0.087 minute inverse. V, let us consider V as a V max equals 0.07 millimole per liter per second. So, we can convert into the mole per meter cube per minute. So, this will be 4.2 mole per meter cube per minute. Now, if you consider there is no deactivation of enzyme, so we can easily calculate. If you remember the equation, that was Km ln S naught upon S plus S naught minus S equals V max into T, and from here all the parameters are given. I can find the value of T. This will be equals to 10.49 minutes. So, this equation has come from the V equals V max S upon Km plus S, and V is minus ds upon dt. So, we integrated it and we got this. Now, in the case of deactivation, what is happening? Minus ds upon dt. What is the V max? V max is K E naught S upon Km plus S, and E naught, as we have discussed, in case of deactivation it will become K E naught K E naught e to the power minus Kd into T S on Km plus S, and if you integrate it, we will end up with this equation T as 1 minus Kd ln 1 minus Kd upon V max Km ln S naught upon S plus S naught minus S. So, from this, if I calculate the value of T, T equals minus 1 upon Kd ln 1 minus Kd upon V max Km ln S naught upon S plus S naught minus S. So, here we will get the value of T as 27.62 minutes. So, what it says, if enzyme was active, it only took 10 minutes, and when it was deactivated, partly deactivated, it required almost 3 times, close to 27 minutes. So, I will conclude this lecture here. So, what we discussed, we started with irreversible inhibition, particularly substrate inhibition and allosteric inhibition. Then we discuss if there is a irreversible inhibition. The irreversible inhibition is basically going to decrease the amount of active enzyme, and then further we discuss the enzyme deactivation due to environmental factors. So, I will stop here. Thank you so much. So, next chapter we will be discussing applied enzyme catalysis.